Lori. Good afternoon, my name is Dominic Bentley. I'm a meteorology and atmospheric science major at Penn State, and today I'll be talking to you about my research project I did with Dr. Henry Housekeeper and Lori Barbarian on comparing SWOT and PACE satellite observations to assess modification of phytoplankton biomass and assemblage by North Atlantic oceanic eddies. So the question is, what are oceanic eddies? In the general circulation of the ocean, these are smaller temporary circular currents of water that occur known as eddies. So these can be formed by turbulence, so large viscosity differences that will meander and shear along this line of confluence that when they pinch off form these cold core and warm core eddies. They can also be wind-driven eddies, so this occurs with net physical forces, where we have a combination of the Coriolis force caused by Earth's spin, along with wind, which causes a net movement of water known as the Ekman transport. Now, particularly in cold core / cyclonic eddies, this net movement of water is away. This is known as surface divergence. To replace this loss of water at the surface, we must bring water from the bottom in a process known as upwelling. Now, this brings nutrients to the surface by raising isopycnals, which are different layers of density in the water, the thermocline, different layers of temperature, and the nutricline, different layers of nutrients. And in oceanography, there are many different questions on how and where eddies modulate productivity, which I hope to investigate. Now, I particularly chose the North Atlantic because we have the warm Gulf Stream that mixes with the cold Labrador current. So there's large differences in viscosity, we have a high shear between these currents, and there's a highly energetic zone due to confluence. So looking at a sea surface temperature map, we can see where our warm Gulf Stream is mixing with our cold Labrador current, creating these turbulent eddies. To investigate these eddies, we're going to utilize the Surface Water and Ocean Topography, or SWOT satellite. This is one of NASA's radar altimeter satellites. An altimeter, basically, it sends out a pulse to measure the distance between the satellite, spacecraft, and the planet. It was launched on December 16th of 2022, so it's a relatively new satellite, and it observes ocean features of 15 to 25 kilometers, which is an order of magnitude finer than previous legacy missions such as the Jason series or the Topex Poseidon satellite. I am particularly focusing on the Karen instrument, or the Ka-band radar interferometer. An interferometer works by, it's a light instrument that shoots a beam of light that splits along a mirror into two different parts. Now, if these are the same distance when they come back, the wavelengths will be complete opposites, creating destructive interference, and we will see nothing. However, as these distances change between the two, we are essentially able to draw the topography of what we are looking at, and particularly, we are looking at sea surface height anomalies. However, since the relative position of these antennas have to be within micrometers of each other, we have raw altimetry observations contain these artifacts. So to correct for this, we apply a crossover calibration, and in doing so, we can now see on our SWOT swath, we have a cold core cyclonic eddy and maybe a warm core anticyclonic eddy. To look inside this eddy, we're going to utilize the Phytoplankton Aerosol Cloud Ocean Ecosystem, or PACE satellite. This is one of NASA's Earth observing satellites that was launched on February 8th of 2024, so it's a very new satellite. It is a hypospectral satellite that utilizes the 315 to 885 nanometer wavelengths at 5 nanometer intervals. It is on a 1.2 kilometer resolution, and we are particularly looking at the OCI, or Ocean Color Instrument, because this supports observations of surface biology. And we are going to use chlorophyll A, which is the green pigment found in phytoplankton that they utilize for photosynthesis. And we'll use this as a proxy for our phytoplankton biomass. So most products are in the testing or provisional stages of the PACE because it is a very new satellite. And due to this, and there are many, many more products yet to come with the PACE satellite. So we tried to find a match between our SWOT swath overlaid onto our PACE scene. And this is quite difficult because PACE and SWOT are very different satellites. They are of different resolutions, different orbital heights, they have different revisit rates, and they are in different swath sizes. However, we were able to find on July 1st a eddy matchup that was with about an hour and a half of each other, particularly this eddy and our sea surface temperature. Looking at the top graph, we have our PACE scene of the eddy, where warmer colors represent higher chlorophyll A concentrations. Looking at our bottom graph, we have our SWOT swath that contains our eddy, where cooler colors represent lower sea surface height anomalies. So, looking at the distribution of our chlorophyll A in the eddy, we have it between around 0.05 and 0.35 milligrams per cubic meter within the eddy, and our sea surface height anomaly follows a right-tailed skew distribution. Looking at particularly in the inner core, we see concentrations between 0.2 and 0.35 milligrams per cubic meter, and our sea surface height anomaly on the much lower end of the heights on a linear distribution. Looking at the outer ring, we have a much wider spread of our concentration between the 0.5 and about 0.32 milligrams per cubic meter, following our sea surface height anomaly following a polynomial distribution. So this can be quite difficult to compare the two, so we wanted to see the relationship between our sea surface height anomaly and the chlorophyll A. And in doing so, we looked at a scatter plot, and we can see that in our lower sea surface height anomalies, we had this much higher concentration of chlorophyll A. And as you increase in height, it will decrease in concentration and a much wider spread, to when we're at zero departure from average of the heights, we're at a minimum concentration of chlorophyll. So some caveats is the provisional PACE data set uses a blue-green band ratio algorithm with hyperspectral algorithms will provide much more robust chlorophyll A estimations than we have currently. And I only viewed one particular cyclonic eddy. But the main takeaway we got from this is that with our matchup, we have a strong negative correlation between our chlorophyll A and sea surface height anomalies that suggests that the innermost part of the eddy is what modulates productivity, most likely through upwelling. Now, my next question is, what kind of phytoplankton can we find in this eddy? And for that, we used an algorithm that was developed by Dr. Sherry Palacios, which is a marine scientist. Her algorithm, the phytoplankton detection with optics, she actually used as her PhD dissertation, which would have been done while she was a SARP mentor. Now, this algorithm works by inverting remote sensing reflectances, or RRS, that we got from our PACE products onto a spectral library corresponding to phytoplankton types that they took through in situ measurements. So we are able to see the proportions of what type of phytoplankton are in our eddy. And in doing so, we see the distributions in it of, there's mostly diatoms, chlorophytes, cryptophytes, and a large amount of non-algal particulates. But primarily, we are dominated by these large diatoms. Diatoms are much larger phytoplankton compared to the rest. And this is atypical because in oligotrophic waters, such as the North Atlantic, they are typically dominated by much smaller phytoplankton. So we are seeing much larger phytoplankton where we normally see much smaller. So overall, we are seeing that the cyclonic eddy is modulating productivity in the centermost with these much larger phytoplankton. Some future work is I'd like to look outside the eddy, understand the distribution of phytoplankton and chlorophyll outside of it, along with look at other eddies. See how cyclonic eddies may differ from this one, or look at anticyclonic eddies. I'd also be interested in looking at other regions of different oceans, see how they might differ. And I would love to use advanced PACE products that are still yet to come in the future, because PACE has such amazing products that they're currently working on. And before I leave you today, I'd like to bring one last food for thought by bringing forth the paradox of the plankton. This was introduced by Dr. George Hutchinson in 1961, an ecologist, and he talked about competitive exclusion, which simply states that given limited nutrients, one organism will become dominant while the rest are driven to extinction. And in doing so, in the homogeneous ocean, we would expect one phytoplankton functional type to dominate. However, we see a coexistence of these other phytoplankton in it. So the question is, how can Earth support such diversity? For that, we turn to the intermediate disturbance hypothesis, which states that given a moderate frequency of disturbances produces the most species diversity. In this case, the disturbances would be the upwelling that is caused by our cyclonic eddies. If we didn't have these cyclonic eddies causing upwelling, we'd have the much smaller phytoplankton dominating, where if we had too many occurrences of it, it would most likely be comprised of the much larger diatoms. But we are in a nice middle of seeing this nice coexistence of other phytoplankton with the eddy. I'd like to thank especially Dr. Henry Housekeeper and Lori for their wonderful help with the project, along with NASA's JPL with their Hypercoast, Dr. Sherry Palacios' Phytotax algorithm, and Dish Shaw for the coding, and along with the wonderful people I have met here in my time in California. It has been an amazing time. Thank you. Any questions? Ben, what can I help you with?
First of all, that was an awesome presentation, good work. I was curious if you thought about or looked at possibly ocean gyres, oceanic gyres. I know are a lot bigger than eddies, so I'm not sure if a larger scale makes it too difficult, but I know gyres can also create a similar effect with either convergence or divergence and either causing a larger.
So I more looked at eddies because I was more interested in the smaller scale, the sub-mesoscale version of it. I believe gyres would probably be very similar. It might be a little bit harder using SWOT because With the size of the gyre, it would be, I believe, probably outside the range, and we'd only get portions of the gyre within the SWOT swath.
This is, well, that's part of the question, but have you thought about maybe looking also at like how the eddies and the types of phytoplankton inside them would change based on like if it's an El Nino year or not?
I am actually interested. I don't think it would be too different. It might be different concentrations of it, but I'm not fully sure. The dynamics of eddies and the how they modulate productivity is very still unknown, which I'm not fully sure. I know that actually the El Nino, the 3.4 area actually does modulate productivity itself because of the trade winds when they increase or decrease. But I'm not sure how they would interact with the rest of the world.
Do you think that the topography of the ocean floor affects the formation of eddies in any way?
For that, I'm not fully sure. I know typically, I would say no, because they're typically based on either wind-driven net physical forces or they're from the turbulence like we were talking about earlier. I would say no, that it does not affect the eddies.
When you were talking about the disturbance severity level graph that you referred to at the end, is that, can that be applied to all ecosystems or just specifically like plankton, ocean ecosystems?
I believe it's a hypothesis that they introduced for any type of ecological species that it is a hypothesis, but it can be applied to just about any ecological diverse species.
Thank you.
So I'm just looking at this and I'm thinking in terms of disturbance, I mean, what about climate change? I mean, how does this, I mean, if temperatures go up, does this thing shift? Does this mean we have lower species diversity? I'm not sure maybe it's not a good question.
I'm not fully sure. Since climate change would be a new introduction of disturbances, it would be one that occurs frequently. So it would actually, I would think, I'm not fully sure, I think it would lead to actually less species diversity because of it. Because we'd have such a high, it would be more on the higher disturbance, because this is a culmination of intensity, frequency, and length. So I believe climate change would actually lead to a more higher disturbance, thus leading to lower species diversity.
I think that's a good answer.
Okay, thank you, Dom.